on the slope. But I just want to tell you that next week your homework's going to be due Wednesday and Friday as well. And I strongly encourage you to pick up your exams if you haven't already. And you can do that at office hours. So, and remember to do this bonus survey 3. It's due this weekend. So let's go to the doc camera and start. And so we left off here on page 120. We're on page 120 here. And remember what we're doing. We're doing confidence intervals for the population slope. So we see some slope right here. We have this probability model where we're randomly drawing from a much larger population, and we get some sample stats, and we get a sample regression equation, a sample scatter plot. And in this case, what we were doing was we were wondering whether there's this negative correlation between drinking and GPA in the population. You know, we think there is, because you think that the more you drink, the lower your GPA would be. But so the null is always the that there's nothing there, that the slope is completely. Well, we're not doing a null yet. I'm getting ahead of myself. We're going to be doing a hypothesis test. Right now, all we're doing is wondering, okay, let's just take a sample out of here of 25 students and see if they have a negative correlation between drinking and GPA. So we did that. There was 25 students, and we did get this slight negative correlation of 0.2. Okay? And then we computed the sample slope, and it's, of course, it's negative, and it's a small slope. So we say, okay, well, that's just our estimate for the slope inside here, that it's slightly negative, but we should put error bars around that, because think about it, every time we take a sample of 25, we're going to get a different slope. So is this slope large enough in absolute value? Is this a strong enough signal? Is this a strong enough signal that we can be 90, that we can be, how sure can we be that the true slope's negative in here? That's what we're thinking. So we said, okay, we have this small sample, and so we're going to use T. And to use T, remember that means we're not going to be using those normal curves. We're going to be using T curves instead. And to do that, to use a T curve instead of the normal curve, we have to remember that means we don't have enough points yet for the n's not large enough for the central limit theorem to kick in, so we're not sure that the probability distribution of our slopes are normal at all yet, unless they come from a normal population. So that's where that assumption comes in. That's, I think, probably one of your homework questions, that you need this normality of the errors when you're using the T curve, because you're using it with this small sample where you don't have enough, your n isn't large enough for the central limit theorem to kick in yet, so we can't, now we have to assume that there's normality of the errors in the population. So that's where that normality of the errors comes in. Yeah?
Professor, can you focus the camera a little?
Can I focus this a little bit? Is this out of focus for you guys?
Yeah, I can't read the text or anything.
Okay, I'll try. Is that better?
About the same.
It's about the same. But you have the text written. You mean you can't read my writing, or you can't read the text, because that's the same as in your notebook?
I can't, the writing's a little.
How about you sit closer? I wish I could do that. I wish I could just sit closer and see. I'm not only kind of blind, but I'm kind of deaf, too, so I'm like Helen Keller, sort of feeling my way through this. And so I want you closer so I can see and touch you. I mean, not touch you. No. Don't put that on oh. I really didn't mean it. I meant touch you with my ideas. Okay, come on up here. Watch. This is going to be this hashtag Me Too moment among one of you. Please don't take it that way. Oh my gosh. Crazy, right? Okay, so anyways, honestly, it's true that I have a difficult time seeing these glasses are not working, but I did focus it. All right, so back to the lecture. All right, let's refocus here. So what we're saying is that we use this normal curve, and we're using the t is what I'm trying to tell you. That's what we're doing, the t distribution. And so what are we doing with the t distribution? So we get this slope, this little slope. We want to put some error bars around it. So that's our sampling error. That's what it tells you. Every time you take a different sample, you're going to get how much is it going to vary? And that's what the standard error for the slope is. We don't know the standard deviation of the whole population, so this is what we're using, standard error plus, and we use it when we use the t. Now, so we got this right here. And right away you should see something, that this is bigger than this. So when we go plus or minus even one standard error, we are going to go, we're going to include 0 in here. So we really don't know that there's a negative slope. So we did that. As soon as you see this standard error compared to this slope, when we add and subtract even one standard error, we're going to include 0 in our interval. So we did that, but we decided to do a 95% confidence interval right there. So we want to be 95% sure that the true slope is within this interval, and so we did that, but you know what? I didn't give you, let's add and subtract that and see what it looks like. So if we take negative 0.02 and subtract, our lower limit for the confidence interval is going to be negative 0.062, but our upper limit, when we add it, is going to be a positive number, 0.022. So that means that 0 is included in there. Since the confidence interval includes 0 here, we can't be 95% confident that there's a negative correlation in the population. In other words, a small negative slope in our sample could just be due to sampling error. And what we're going to look at very shortly in the next chapter is how a 95% confidence interval that includes 0 is equivalent to not rejecting the null. Because why? Because for a two-sided, 95%, and this would be true with t or z, but we can see it, let's just do it with z. Well, it doesn't matter, both of them are symmetrical like this. So if you have a 95% confidence interval, that means, and here's 0 right in the middle, that means 2.5% is on this side and 2.5% is on that side. So if your 95% confidence interval includes 0, that means it's inside here, and that means that's the same as you can't reject the null. You're not on either side here. If the 95% confidence interval, if the limits of it didn't include 0, like it was from here to here or something, it didn't include 0, or from here to here, then it would be the same as rejecting the null. Rejecting the null. Because, right now we're not 9, so let's write, that's what that says for the two-sided. And how about for a one-sided? A 95% confidence interval for a one-sided, like in our case down here, less than 0, it would be at alpha, if we knew ahead of time which direction, then it would be a 95% confidence interval would be equivalent to a one-sided test at alpha equals just half that. That's the same as 5%. That's the same as 2.5%. Okay? Does that make sense? So let's do the So now that's with the t. So let's just compare it to the z here. And so for the z, I just want to ask you a question. Do you think this confidence interval here for the z, do you think it's going to be wider or narrower? Will it be wider? Will you have more uncertainty with the z or less? What do you think? It's not going to be wider. It's going to be narrower. Remember, z is narrower. So let's do this one as an iClicker. So let's say we want to do, first of all, let's just set it up. So you want to do a 95% confidence interval. Let's just do z this time and see what difference it makes. So if we were going to be using z, we'll just do the same thing. It's the sample slope. So it's going to be negative 0.02 plus or minus, and then we'll have what in here? We have to have z star, and we could use 1.9, let's just use 2 instead of t star, right? It's going to be the same thing. I'm just comparing it. Okay, so right here is t star, and now we have z star, which is always smaller, and that's why it's going to be narrower. Plus, we're not going to use SE. Well, let's just use the regular standard error, okay? So I should write this. This is equal to the sample slope, that's what we're doing here, plus or minus z star. And then we could use SE plus, but people generally just use SE, all right? So if we wanted to get SE, and we know SE plus is, where is SE plus? We just did it over here. So that's the SE plus. And so what are we going to do? Instead of divide by 23, we'll just divide by what? 25. So that's equivalent to which one? This is going to be your iClicker. If we want to change that, want to get rid of that 23, and we want to replace it with a 25, what would we have to do? We want to get rid of that and replace it with an n, square root of n in the denominator. Okay, so let's just go to that, and you can think about it while I'm switching to here. And let's start it. Okay, did you pick one? Let's stop this and see which one you picked. Great, that's right, and let's look at it. So let's go back to the document camera. And looking here, so this is your answer right here. And what are we doing here? Okay, so we want to get rid of this 23. So we're going to multiply the numerator by that and then divide and replace it with this. Another way to think of it is, look, SE is smaller than SE plus, and this number is less than 1. So that's what you want. And then you can multiply it by 0.0204. And I got, when I did that, 0.0196. That's SE. So that's what I'll put in here. 0.019. Did I say 6? It's 6 here. 6. Okay, any questions on that? Can you see that? Can you see my writing now? I'm writing with a darker pen. Okay, good. I think that might be the problem, that I didn't use the felt tip before. All right, so let's just get, so if we, now we get a confidence interval that's going to be a little bit narrower. It goes from negative 0.59 to 0.192, okay, as opposed to this one. It's a little bit narrower. And if you reject the null with this one, if zero's included with this one, then 0 here is still included. It's not necessary. This one's wider, but it's still included here. So that's the idea. And any questions on this? All right, yes?
Why we don't use SE plus to calculate the interval? Why we use SE to calculate the interval or not SE plus?
She said, why am I using SE instead of SE plus? To be more accurate, I could use SE plus. There's nothing wrong with it. SE plus is always a better estimate of the unknown standard error in the population, standard deviation. But why am I doing this? Just because it's generally, by the time n is large enough to use Z, you usually use SE. It wouldn't be wrong at all. And you'd still get a narrower confidence interval, because the narrower confidence interval is always going to come from the Z star. Does that make sense? Okay, good question. Here we go. And now let's just make sure that you understand the summary here, because we did it in 2 pieces this time. We broke up the chapter, so I just want to make sure you understand this. Okay, so for large sample sizes with the independent, identically distributed errors, this is assumptions number 2 and 3, equal variability across all the x's. So this is number 2 assumption. That's independent, and this right here is number 3 assumption. And of course, you need number 1 to even begin to do this. You need number 1, which is linearity, to even begin to do this. So, and we can, the probability histogram for the sample slope follows the normal curve, so we can use the normal curve to build confidence intervals here, as long as for large samples. But now when you have, and then, here's the form of the confidence interval. But when you have, why is it doing that? I'm really sorry. I'm pressing autofocus. Thank you. Okay, so now for small samples, when we have small samples, this is when you need that 4th assumption of normality. So that's where it comes in, right here. Because now you have to assume your sample isn't big enough for the central limit theorem to kick in, so now you have to assume normality, okay? So that's the idea. And so it's only needed, assumption 4 of normality, number 4, is only needed for using the t-distribution. Okay, and you're going to see this all the time if you're, independent, identically distributed errors with normal 0 sigma squared. That's what you'll see abbreviated as IID. Have you seen that in other classes? IID, that your errors are IID normal 0 sigma squared. Okay, and now these degrees of freedom. All right, so the degrees of freedom are n minus 2 here. Why? Because degrees of freedom refer to variance around your model. That's what it refers to when we have to estimate the variation around the model. So when we're estimating a mean, that just has, the model is just described with one parameter. It's just, once you know one point. Okay, degrees of freedom to estimate the variance around the mean is n minus 1 because our model has one parameter, the mean. So once you have that mean, then it doesn't even make sense to talk about variation around 1 point. You can estimate a mean with 1 point, but you need at some other points. So the variance, the n minus 1 points around the mean are the degrees of freedom. Similarly, with a line is described by 2 points. So you need 2 points to even describe the line. To get variation around the line, you need more. So n minus 2 points are around the line, you can think. So the degrees of freedom to estimate the variance around a line has n minus is n minus 2 because the model, the line has 2 parameters. So we think it's described with an intercept and a slope. Those are each parameters that we're trying to estimate. Whereas with the mean, there's only one parameter, and we're going to be adding more slopes. For example, if we added another slope, that would be a plane. We'd have a regression plane, and then we'd have n minus 3 degrees of freedom because a plane is determined by 3 points. So this idea of degrees of freedom is going to come up a lot. So I just wanted to explain it here. Any questions on that? Oh, all right. So now, and I should just tell you before you get that this right here, this will be given to you on exam 2. This, the standard error, this one's going to be given to you. This one is not going to be given to you. This one is not given. This one will be given, and this is not given. You'll have to know this one from that one. All right. Now let's go to significance tests for the slope. So just how, we did all these significance tests, but now we're just going to do it for regression, for slopes. We're going to, the null is going to be that the, slope's 0, or that, there's nothing to our model, and then we're going to look at, do a significance test, and actually use a Z and T test. So let's think about it. So why would we do that? So sometimes instead of just finding confidence intervals for the true population slope, we want to get a p-value for the null hypothesis that the true population slope is 0. So we're going to ask ourselves, do the usual thing. If it was 0, how likely would it be to get such a big difference from 0 just due to the luck of the draw? And that's going to be our p-value. So you might guess that you just take your confidence interval around the slope and ask whether it includes, your sample slope includes beta equals 0. If it's outside the 95% confidence interval, for example, we'd reject the null. And that's what we just saw. So the procedure would be exactly the same as what we've been doing. We check our assumptions, linearity, independence, equal variance, and more or less normality, depending on sample size, by looking at the residuals. And then if that looks okay, we are going to look at the statistic that you would think that you'd look at. T is equal to the observed slope minus the expected slope over the standard error for the slope. That's what's generally done, even with large samples. But we'll see that with large samples, we might as well use a Z. But this is what's generally done. And this, we can always, that's usually under the null, that's equal to 0. So the expected slope is equal to 0 under the null. So we end up, here's the Z version of it. Okay? We're going to do both. So now the only difference between these two is here's the square root of n, here's n minus 2. Now, if we do this, it simplifies to this. Look, it only involves, the statistic only involves r and n, because this cancels out, see? And it simplifies to that. So that's the idea, and then we'll attain a p-value. by either looking at the normal curves with n minus 2 degrees of freedom, or just looking at the normal curve. Okay? So if we were going to do a 95% confidence interval, I can just draw it here. For a two-sided test, this is equal to 2.5% and 2.5%. So I should give you this as a iClicker. So what if a 95% confidence interval, we'll write it down. Let's look at it on the PC here. So this is our next iClicker. And let's do this. Okay, let's see what she said. And we'll stop this. Good, that's right. And let's go back to the PC. To the document. All right, so a 95% not including 0. That means it's outside. It doesn't include 0. So we're outside that region. That's the same as rejecting the null for the two-sided alternative here at 5%. Or at what? For one-sided, if we specified it ahead of time, it would be the same as rejecting at 2.5% for the beta is either beta 1 and the population slope is either greater than 0, that would be 1, or we'd have to specify one of these two. Okay? So notice, this is the important thing, that our test statistic end up only involving R and N, not SDY and SDX. So does this procedure fit with what we said hypothesis testing means? Does it give the right answer? Yes, it does. So let's do a hypothesis test on the drinks GPA example instead of the confidence interval. So we'll do that. So now we're interested in finding out whether or not there's a negative slope in the regression equation for predicting drinking from GPA among all UI grads. But we don't have the time and money to sample all 28,000 students. It's the same deal. We don't have the time and money to, sample them all. So we take a random sample, and we're going to do 25 students, and with a confidence interval, you make an estimation, and with a significance test, you are making a yes or no decision to reject the null. But they're pretty much equivalent. Okay? So instead, we're doing the same thing, and we find a slope. We can use exactly like what we did before among the 25 students. So is that slope strong enough to conclude a negative slope in the population? So we'll do a significance test. And here's our sample stats, and assume the 4 assumptions hold. All right, we're just going to assume that. And here's our sample regression equation. We're going to start using formal language really soon, so I'll just write it that way. So what do we have? We have our prediction equals, usually we write it this way. But I wrote it the other way. So this is where we're going to put the slope, and this will put the intercept there. Sorry, I did it the wrong way. I did it in the mx plus b form. It really doesn't matter. But, all right, so how did I get this slope? Just to review, and you do need to know this, the sample slope is equal to what? R times SDY over SDX. And now, which is y and which is x? Y is always what you're predicting. And what are we predicting? Oh, we're predicting, look at this mistake. We're predicting GPA. I'm sorry. I'm glad I noticed that. GPA from drinking. The way I said it, I have X and Y reversed. It makes more sense to the more you drink, the lower your GPA, rather than, well, I guess the lower your GPA, you're just so depressed you go out and drink. It could be that way too. Either one. But we're predicting GPA. So this is Y. GPA is Y, and this is X. I'll just, to remind you, Y is the variable you're predicting. It's the dependent variable, dependent on X. All right, so that's what we have, and so now we do it, and we say negative 0.2 over the ratio of their standard deviations, which is 0.5 over 5, and that's where we got our negative 0.02 last time. Of course, it's the same. We're not doing anything different. And then if we want to get the intercept right here, so let's plug in our slope. And now we just want to solve for the intercept, and what do? Well, we know we plug in the point of averages. That's what we do. So you plug in point of averages. So average GPA, 3, is equal to negative 0.02 plus this is times X plus this one, beta naught. And so what do we get? 3. And what do we do for X? We have to plug in 10 for X. Sorry, that's messy. That's a 10 for X. I can write it underneath. That's what you want. So now we have 3 equals negative 0.2 plus what? So that has to be 3.2. So any questions on this? This is what we did before. So that's all. Now we've got to formulate a null and an alternative, and we're going to use a one-sided alternative because we think that we're going to get a negative slope before we start. So here's even before we looked at that, we're doing this because we're wondering about, does this negative correlation hold up? It would be really kind of crazy to think the more you drink, the higher your GPA is. So there's our null, and so we have to set up the probability model under the null. So under the null, what is it? So we have this null box, or null, you can call it a box. It's really like a null model because it's a population scatter plot for the whole population. And it has lots and lots of points, 28,000. So in the population it's all positive here, we have all 28,000. This is drinks. This is GPA. And we have 28,000 points, one for each student at U of I. For each U of I undergrad. Now remember what our null is saying. Our null is saying that it looks like that. The null says that this beta 1 is equal to 0 in the whole population. So that means our best prediction, the slope is 0. And if you plug a 0 in here, you'd get what? GPA equals 3.2. That our best prediction is the average GPA, average right here. No matter how much somebody drinks, what are we going to predict? The average. That's what it's saying. And that's the same as what? Same as R equals 0 in the general population. There's no correlation, and our best prediction is just the average. This is like the average right there, no matter what. That would be our regression line. Now, of course, we're not going to get that exactly 0 slope when we do a random sample. But now we look at, now we have our sample scatter plot that comes from randomly taking out, just randomly drawing what? N equals 25 randomly drawn points from here, randomly drawn students. And then in our sample, this is what we got. It looks very close to 0, but it's not quite. We got a correlation of, this is what we got right here. So this is our sample regression line. And here we got R equals negative 0.2, and our sample slope is negative 0.02. All right? And that's drinks versus GPA. But this only has 25 points, and I drew too many. This one has tons. Imagine, tons. This one only has 25. Okay? So there's only 25 points in there. And so the idea is you get this is what we see, and we're saying how likely is it to have come from here? That's what all significance tests are. Because I noticed on the exam, some people got the sample and the population mixed up, or with the box. This null is always about the whole population, and this is about the randomly drawn tickets from it. Unless you're talking about gambling, where you have a specified odds that don't change, then you can. All right, so this is drawing, and they're drawn without replacement because we have separate people. So now we'll just compute a z. Let's just do a z and a t. So what would we do? We'd say our observed minus our expected slopes over our standard error for the slope. And we could cross that off because we know that's 0. And now, what would that be equal to? That would be equal to, these are slopes, so we have our observed slope. So that's R on the numerator times S dy over S dx. And in the denominator, what is it? It's 1 minus R squared times S dy, that's the standard deviation of the errors, over the square root of n times S dx. These will cancel out, and now that will simplify, multiply top and bottom by this reciprocal, and we end up getting what? That will be R times the square root of n over 1 minus R squared. And we can do that. R is negative, what's R? R is negative from here, negative 0.2, way up here. So it only involves this. All you need to know is this and n. From those two, we can get the standard error. That's what it boils down to. You only need those two. So we have negative 0.2, that's r, not the slope, times the square root of 25 over 1 minus negative 0.2 squared, the square root of that, 1 minus r squared. And I did that, and I got a negative, because there's a negative here, 1.02. And that is the z. That's our z. I mean, we could do the same thing. How is our t going to change? It's going to be exactly the same thing. Where is it going to change? Instead of this, a t will be what? The SDYs in the numerator, it's going to be the same. It's just going to, it's going to be the observed. I can do it if you want. Observed slope. It's the same thing minus the expected slope under the null. That, and that's 0. And then the only difference is it's going to be the standard error plus of the slope of B1. Right? And so then when we do that, we're going to get the same thing in the numerator. I'll just do it again. STY over STX. And the same thing in the denominator, except for what? Instead, we'll get the square root of 1 minus r squared times the standard deviation of y. That's fine. The only difference is going to be what? The square root of n minus 2 over SDX. Those cancel out, and here's our statistic. It's the same exact thing, except we're going to have what? When we simplify it, we'll have r times the square root of n minus 2 over 1 minus r squared. So that will look just like this one. It'll be negative 0.2, but a square root of 23 here, and the denominator's the same. The square root of 1 minus negative 0.2 squared. So it's going to be smaller, right? Because we're multiplying by square root of 23 instead of square root of 25. And so we get negative 0.98. And that is our t. So that's the only difference right there. And it's all because, we're taking into account that we're estimating the standard error of the deviations right here. So this is the difference right here. But the bigger difference is when you look on using that curves, two different curves. We could use this statistic. We could have done the same thing for both of them. The difference is really which curve you look at, because that curve is shaped quite differently if you have a small sample. So let's do this. So now, here we're going, okay, so we just did the calculations on the other page, so this is describing the reasoning, and let's write it down. So we got this one, and this one we got that. All right. Now, compute the p-values. All right, so the p-value for the z is very easy. There's just one normal curve. So what we're doing is, here is the z, and underneath it, right here, would be the slope. And the expected is 0, and we want to know how weird negative 0.02 was on here. And it turns out it matches up. It's just slightly over negative 1, and it matches up with, this is right here, with a slope of negative 0.02 on this curve. All right? And when I did it, and so we're doing an alternative that's one-sided from the previous page, remember? We have a one-sided alternative right here. So we're just looking at this tail, and we get a p-value here. I did it on the p-value calculator because I wanted to get it more exact, and I got 15.39%. If it was one, it would be more like 16%. It's a little bit less. Okay? And now, how about this? Well, now it's problematic because now we have to look on a t-curve. Which t-curve? So this is going to be for what? The t with how many degrees of freedom? We're going to look with 23 degrees of freedom. Now, let's remember why, because we're going to be moving ahead to multiple regression. So just remember what our model is here. It's this line. So our model is a line. So we have y is equal to beta naught plus beta 1 x, and then we're going to have some error here, right? But this is two parameters because there's two things we're estimating. So we'll say two parameters. P is equal to 2 parameters. This is a parameter that we're estimating, and this is a parameter. The betas, not these errors. These two are parameters. P is equal to 2 parameters. And n is equal to 25. And our degrees of freedom is always going to be equal to n minus the number of parameters. So in this case, it's 25 minus 2, which is 23. Because 2 points determine a line. All right. So once you estimate those, the rest are free to vary. So now we just have to put it, now this is a different curve than this one, even though they look identical. This one's going to be a little shorter in the middle and fatter. And this one we're doing basically just right there. That's what, on the t-curve, this is negative 0.98. They look very similar. But, and as beta, that is negative 0.02. And if you look on the t-curve, they're very close because we have a high degree, 23, it gets really close to the normal curve. But we're going to have, it's fatter in the tails. T is fatter in the tails, so we're going to get more percent here. And we have 16.86%. So even if we looked at the exact same statistic, it would be fatter tails, and we'd have a bigger p-value. So you need more evidence to reject the null. So that's the idea. So we cannot, small values of p are evidence against the null. We cannot reject the null, which agrees with our confidence interval that included 0. Cannot reject null. We can't rule out that beta 1 in the population is 0. It's in our confidence interval, and we cannot reject the null. We'd have to go out further. So that's the idea, and wow, we are done with this chapter. That's all I planned to do. Maybe I should just go ahead. I didn't realize this is all we were supposed to do. Why don't we just go ahead so you can just a little bit. I didn't realize we were going to do that. Yes?
How do you know that they're one-sided?
How did I know this was one-sided? I'll write it down here because we were given here, I didn't write down the alternative is that we set this before, that it's less than 0. So let me write that down for both of these. Our null is that our slope in the population is equal to 0. And we think, before we even looked at the data, that because of just our experience, that the more, we thought there'd be a negative correlation between drinking and GPA. So we're only looking, that was that, and that's why we're only looking at the left-hand tail. Does that help? Okay. So now let's go to something called analysis of variance. So this is going to be we're going to be looking at analysis of variance a lot. And what is it? Is that needs to be focused more? Is that good? Okay. So this is chapter 27. And what are we doing here? So this analysis of variance, and sometimes you see it abbreviated ANOVA, it basically provides this basic framework that can be used for all predictive models as long as basically our 4 assumptions are met. What does it do? It checks whether adding more parameters to a model, like adding slopes to a model, making the model more complicated, if it improves the accuracy of the prediction significantly more than would be expected under chance. And it yields this statistic called the F ratio. So what is it doing? That's the general idea. So here, you can think of it this way. We're adding one parameter. We can estimate, in this example, we could estimate GPAs just by the average. Is it going to help to add in this information about how much people drink or not? Does that improve our model? Is there anything in that slope or not? That's the idea. So, or could we do just as well if we just predicted the average GPA, no matter how much people drink? Maybe drinking is just like, makes no more difference in height in terms of GPA. So, so the idea is, now why do we need something besides what we just did? We have a z-test for that. We have a t-test for that. Why do we need anything else? Well, you wouldn't unless you want to do a general, if you want to go further, and we do. We want to start adding more slopes. So I wanted to introduce this idea of analysis of variance in the 2D, so we can draw it, like with a graph. That's what we're going to be doing, and you can understand it better than when we move into more dimensions. So why do we need something else when we add more? Let's say we wanted to add homework. Let's say we wanted to add gender. We wanted to make a better model to improve our predictions. Well, how would we assess the fit of that? It would be very hard with just a single signed number like z or t, because some of the slopes could be positive, some could be negative, and we need a way to combine the collective effect of all the slopes that we're going to be interested in. And this should remind you of why we use the chi-square when we had more than just 2 categories, yes and no. When we had multiple categories, how were we going to assess the fit of the model? When some to take into account all the groups when we had multiple categories. And so we're going to be doing the same thing here. In fact, we're going to be using an F statistic, which as n gets large is the same as a chi-squared statistic. So we're going to look at F and chi-squared statistics. When n's large enough, they'll be the same. So they bear the same relation as z and t. So we're going to bring back the chi-squared statistic, and it'll be a lot of fun. We're going to tie a lot of things together. But first, let's figure out what's going on here. So let's just do it in the context of simple regression, where we can understand it better. All right, so for simple regression, analysis of variance is just another way to get the same p-values for the slope that we can get from z and t-test. But it's a good idea to show how it works now to understand how it can work in more complicated models. Okay, so here's our simple linear model, intercept plus 1x, 1 slope, and let's just assume that the errors are normal. These are 3 assumptions about the errors. Okay, and so let's look at some formal language again, because now we really need it. Okay, so we're going to say y is an observed value of y. Y with the little hat on it is going to be predicted, and y bar is the average of the y's. All right? So, remember when you take a standard deviation, what do? You get all the deviations. So that's for each y, we subtract off the average and we square them. Then we sum up all those. And if we divided by n, it would be the variance. And if we took the square root, it would be the standard deviation. But this right here, before we do that, is just the sum of squares total. All right? Just the sum of squares total. It's before we take the mean, take its mean, it's the variance of y. Okay, so this is just that. And this is the sum of squared errors. So why is it? What is this? This is your observed minus your predicted, right? Y minus y hat. Observed minus predicted is your error. Remember, if we added them all together, we'd get 0. That's why we square them. Same with this. That's why we square them. Then you take the sum of those, and that's the sum of your squared errors. And if you take the average of that and the square root of it, it's the root mean square error. Okay? And here's our null, and here's our alternative. Now, for analysis of variance, we're squaring everything, so we only have two-sided alternatives. Only because we're not looking, how could you distinguish when you're squaring things? So you only have two-sided alternatives. You know, they're not going to look two-sided because our statistic is going to be always positive since we're squaring everything. But they're equivalent to the two-sided alternative. They can't distinguish between less than and greater than. It's just not equal to. All right, so does adding a slope make a significantly better prediction than just using the average? We already tested that using a z and a t. We're doing the identical thing. But you'll see we'll get a similar answer when you do it. This is the same as asking, does it reduce our prediction errors significantly? Now, how does ANOVA deal with this? Because we have to do all these sums of squares here, and we can't boil anything down to a single sign difference, right? We're going to have to do something very similar to basically what we're going to be doing is a z squared or a t squared here. We're going to have to look at variances, squared differences, instead of just the observed minus the expected over a standard error. We're going to look at breaking up the variance of these y's. This is the total variance. This is the variance of the y's. Well, not really the variance of the y's. It's the sum of squares total. If you divide it by n, it would be the variance. Okay, so you look at the total variability. That's why I'm calling it n times the variance is equal to the SST, okay? SST divided by n is the variance. So this is just the variability in the y's, right? That's what you're trying to, and then we're breaking it into two parts. The variability explained by the model and the variability left in the errors. What do I mean by that? Well, for an individual observation, what does this mean? This means that the distance that the y is from the average can be broken up into two parts. It can be broken up into the predicted minus the average plus the observed minus the predicted. You can see this is just by algebra. This, you have those would cross out, and you have y minus y bar is equal to y minus y bar. Right? I mean, this is very simple. So, the observed minus the average is the observed y. This is the predicted minus the average. Yeah. And the predicteds cancel out. All right, so can we do that? Can we just do that to squaring everything? No, you can't. You can't just square this side. You'd have to, you'd get cross terms. You can't just say square this is equal to squared plus squared. No. But can we do that? No, not algebraically, but in this case it works out. And you can see the appendix for the proof. And an easy way to remember it, so let's look at this partition visually. So what we're going to be doing basically is we're going to say, okay, you have this total variability of the y's, right? That's what we're trying to explain, the variance in the y's. If there was no variance in the y's, that would mean, like, for example, finals, every single person got the same final score, and there'd be nothing to predict. You're trying to predict the distance above or below the average for everybody, right? That's what you're trying to do. So you want to predict the variability of the y's, and you're going to break it into two parts. One that can be fit by our model, and one that's left in the errors. And then we're going to assess the ratio of these two, basically. How this is like the strength of our model, this is like the strength of our errors, and we're going to come up with a ratio, or an adjusted ratio of these two, to see if it's large enough to reject the null. If there's enough in our model that's more than just random chance. If there's some signal we can detect inside the model, or if it's just if this model's no better than random chance. That's the idea of how we're going to do the test. But first, let's just picture it with 3 points, or we'll figure it out with 3 points, but first let's just visually look at it. Okay, so what are we doing here? So here is the same regression equation that is finals predicting exams, right? And here's y bar. This is our average. This is if r was equal to 0. We don't have if r was equal to 1, but we do have the regression line here. This is our regression line. This is how we're making predictions. So these are these are our predictions. And then these points are just the y's, right? So we can focus on this point here, D. So person D got an exam score of 92, and then a final score of 95. So that's that person's point. And the regression line predicted he'd get an 80. So there's his y hat right there. This is his y actual. That's his predicted. And this right here is the average. And what we're doing here, when we're breaking this up, we're saying, okay, so we're breaking up the total into two pieces. Here's the observed minus the predicted. That's this distance he is off the regression line. And this is the predicted minus the average. So this is how much using this regression line is better than using the average. And this, like right here, is the total. So you can see what we're doing here. So all we're doing is breaking up this point that's 20, this is 21 points. It deviates 21 from the average, and we're just breaking it up into two parts. We're breaking it up into the part that's the model, how much the model helped from the average. That's 80 minus 74, plus our error. What is actual is that's 15. I should color code these. So this is this one, and this is this one, and this is this. And we're going to do that for every point. So let's just look at the points now. So if we did that for every point, our errors would be like, this one's off the line, right there. This is this, right? And the green is that. We can do it for all of them, so you can get a visual. This, right, oh, this is, this has just a little error. This has a huge error. Wow. And this has no error. All right, so then this is all model. So this one looks kind of weird. Where's the green part on here? The green is just this, right? these two things are going in opposite directions. So it's saying, after you it's actually that, because this one's going down and this one's going up. And they're in opposite directions. Those will subtract off. So that's the idea. So when you're looking at this, what we're going to be doing are these arrows, like is how comparing our blue, how well our model does versus our errors for all the points. And we can't just add them up because they'd sum to 0. So we square them. And that's the idea. Any questions on that? So let's just do it for 3 points, and then we'll be done. You'll see how it works. All right. So let's look at this. So we've got 3 points, this point, and this point. And now we have to get the average. So let's get the average of, here's our 3 points, just the average of the y's. We're going to take those 3 y's, 1, 6, and 5, and divide them by 3, and we get 4. So there, right here, is y bar. And now, what's our model? Our model is this regression line. Where is it? There it is. There is our model. So that is our regression line. So we better get the, this is like the y. We need to get the y hats. So let's think about it. So what are our y hat, x, we get an x and we get a y hat for it. So for each x, like x1, for 1, our y hat we'll just put is 2. It's just twice x. So for the next one, it's 4, and for the next one, it's 6. So that's what our prediction is, right? So we've got those, and now we can fill this in. All right, so our points are, I'm looking at just the y points here, right? 1, 6, and 5. Y, 1, 6, and 5. Those are our points. And we're subtracting off the average for each one of them. This is what we do. These are our deviations, right? So we get our deviations, and we get what? -3, and here we get 2, and here we get 1. And if we summed them, we'd get 0. So you know you did it right, and that's why we're not summing them, so we're squaring them. So you square each one, and we get 9, 4, and 1. So we have 14 is our total SST. So that's our SST. If we divided it by 3 and took the square root, we get our standard deviation. Now we are going to break it up into 2 pieces. And the first one is going to be what? Our predicted, which are right here, 2, 4, and 6. These are our y hats from the model. So that's 2, 4, and 6. And from each one of them, we're going to subtract off the average, right? And now we'll get these. How, excuse me. So this is -2, this is 0, and this is 2. And check that those sum to 0. Otherwise, you didn't do it right. Okay? I should write that down. Check that each column sums to 0 before squaring. Otherwise, you made a mistake. All right, so that sums to 0, so that's what we're squaring them. And we get 4, 0, and 4. Now, at this point, you know this has to be what? 6, because they have to sum. That's the point. So we know this has to be 6, but let's check it. All right? So let's make sure we did it right. Let's check it. So now what are we doing? These are our actual points again, 1, 6, and 5. But now it's our observed minus our predicted, which is 2, 4, and 6. All right? So that's the idea. And we're going to square them. I should square these, show you so you don't forget. Okay, and so here we have what? -1 before we square it, 2, and here we have 1, -1. And now they sum to 0, and now we square them. And we get 1, 4, and 1, 6. It works out. And on the picture here, what were we doing? Well, here is the blue parts. This had no model here. And the blue is its distance right here to the regression line. And then here's our error. And you can see how they match up here. Okay, so that's the idea. And you'll have a homework problem just like this. So you can do it for 3 points, but what if you have lots of points, you can see this would be incredibly tedious to do. Incredibly tedious. So, but in preparation for this, the ANOVA table is a handy way to illustrate how the sum of squares are partitioned and to compute the F ratio. So we're just going to do this here, and we'll explain it next time, what this F ratio is in more detail. So we have 2 parameters, right? Those are the population, they're estimated. Okay, we've got 2 right here. So remember, n is equal to 3, and our number of parameters is equal to 2. Okay? From there. All right, so we've already figured, let's put this here. The sum of squares total was 14. That goes here. This is 8, and 6 equals 14. Now the degrees of freedom add up too. We have n minus 1 degrees of freedom. What's n minus 1? That's 3 minus 1, 2 degrees of freedom. Now each one of these has their own set of degrees of freedom. This, for the model, it's the number of parameters minus 1. So that would be 2 minus 1. This is 1 degree of freedom. And for the errors, this is what we've been doing. Whenever we do n minus p for the errors. That's why it's n minus, this is what we're, sampling error. This is where we usually think of this degrees of freedom in this row. So we have 3 minus 2 for a line, n minus 2. But all of these have these degrees of freedom now. And now, and this is like the total. This is what you're used to when you estimate a mean, n minus 1. All right, so now to figure out the F ratio, it's not the sum of squares over the sum of squares errors. They're tweaked by their degrees of freedom. So they're divided by each one of these. So it's the mean square. So 8 divided by its degrees of freedom. Well, that's still 8. In this case, it's the same. 6 divided by its degrees of freedom is 6. And then the F ratio, which is going to be our test stat, is the mean square model over the mean square error. In this case, it's 1.33. And that's what we're going to look up on an F curve. And I think this is a good place to stop. So have a great weekend.